Here's your video on algebraic continuity. Just like with limits, where we did limits by a graph and then algebraically, we already did continuity from a graph, and we learned the types of discontinuity, which is infinite, point, or removable, and jump. So now we're going to do algebra continuity. So that means we're just not going to be looking at a graph here. So you'll be given various different functions. In this case, we're going to start with a piecewise example, and your job will be to determine at a certain point, which in the definition is referred to as A, is our function continuous? So are there no holes, jumps, gaps, asymptotes, etc.? So for our first example, we have a piecewise function. We have a rational function, and a function that kind of looks rational because there's a fraction and a denominator, but really this is just a cubic because they're just dividing by a constant. So in the last video, we established this right here. This is the formal definition of continuity. And we really just have to go through these three pieces and check them off one at a time. And in order to be continuous, all three of these pieces need to be true. So let's go ahead and start with f of a existing. So at a certain point A, in this case, which is 3, does our function actually exist? Is there a point somewhere at 3? Now notice that 1 and 2 are interchangeable, so you could start with 2 and then do 1. I usually start with 1 and then I go to 2. It really depends on the problem. So for this case right here, we're going to start with proving that f of 3 exists. So I'm going to look here at my domain restrictions, and the only function in my piecewise function that I can plug 3 into is the last piece, because that is defined when x is 3. So all that I did right here, I already wrote it out because it's such basic math. I plugged 3 into my cubic at the end, and I saw that the function value at 3 is 8. So that means I have a closed dot when x is 3 and y is 8. So I've established the function at 3 exists. Good to go. Now I need to prove that the limit, the overall limit at a exists. So the overall limit at 3 exists. That means the left-hand limit must equal the right-hand limit. So we're going to go ahead and do that on the next slide. Limit, I am going to try direct substitution first. Remember, you always do direct substitution. And whenever I do direct substitution, I notice I get 0 over 0. First of all, 0 over 0 is indeterminate form. Indeterminate form. And it means you're not done. You have more work to do. So one way that we're going to do this, in this case, is factoring. Remember, you could do this with conjugates if there's radicals, or if there was a complex fraction, it would mean you should have to simplify your complex fraction. Either way, you're going to have to cancel something in order for this to work out. So let's start from scratch here, and let's go ahead and try and cancel something. The ideal way to show your work is to start by just saying the limit as I approach 3 from the left of the function. And then I'm going to say the limit as I approach 3 from the left, and actually fill in which part of the piecewise function I'm using. I'm using the first part because that was defined when x is less than 3. And I haven't plugged in yet, so I'm still writing the limit as x approaches 3 from the left. And I know some of you are going to hate writing this, but you're going to do it so much, it'll just go quick. So let's see, that would be positive 5 and negative 3. Oh, there we go. There was a hole at 3. 3 from the left of x plus 5. I'm still writing this because I haven't plugged in yet. Now I'm going to plug in, and I get 8. So as I come from the left, I am approaching 8. That is the intended y value. So now let's go ahead and do it from the right. So I did the first one. This is the quick one. You just do direct substitution. Whenever there's an x, you plug in 3. And I get 0 over 0 again, so that means I should try factoring again. And I'm going to try factoring because I have a quadratic. So fill this in with me here. I'm approaching 3 from the right this time. This was the function defined whenever x is greater than 3. So we're coming from the right. All right, so I did the general function, and then I wrote the actual function I'm dealing with. A lot of times people forget to actually put an argument after the limit. Like they'll put limit as x approaches something and then equals, and they won't actually put f of x. You have to have the limit of something. You can never have a limit and then a blank space there. So for these, let's do -3, +1. Oh, more canceling. So now I'm going to write limit one more time because I'm going to get ready to plug in. I have 2 quantity x plus 1, which is 2, 3 plus 1. 2 times 4 is 8. Oh, that's good news. Since the limit as x approaches 3 from the left equals the limit as x approaches 3 from the right, therefore, the overall limit as x approaches 3 of f of x not only exists, but also equals 8. And that's really good news because whenever I did the function value at 3, I got 8. So check it out. The function value exists, the overall limit exists, and they are the same. So my actual y value and my intended y value are the same exact thing. So to summarize it here, our limit is 8. Our function value is 8. Now I know the limit is 8 because the left and the right hand limits match up. Since the actual y value equals the intended y value, by definition of continuity, the function is continuous at x equals 3. This is how you want to be stating things on the AP exam. You should always be citing some kind of formula or theorem and saying where it occurs. All right, so I get that little conclusion written down, and let's move on to example 2. This is an AP level problem. It's slightly more involved than the other one, and that is because we have unknowns here. And this one is worded a little bit different because they're telling us the function is continuous. So notice in the other one, we were trying to prove that it was continuous. So we couldn't assume this. We were trying to show that. For this example, we are assuming all 3 of these are true. And we're going to go backwards to find constants B and C. Same exact theorem that we're using, just slightly backwards. So normally I would start with f of a existing. But the thing is, a is 2 here, because that's where I'm interested. Right there. And the function's defined it to be c. So that's not really helpful because I don't really know what c is. So all that this tells me is that f of 2 is c. And I know that it exists at c, but I don't really know what c is. So let's go ahead and move on to the limit as f of x approaches a exists. Now I went ahead and wrote this up because it's the same exact notation as the last example. So pause the video and write this down, and then I'll explain. Since we know the function is continuous, we know that the limit has to exist. Since we know the limit exists, we know that the left-hand limit and the right-hand limit have to be the same. Okay? Because the limit exists, the limit from the left has to equal the limit from the right. So I went ahead and I did the limit from the left of my function. Then I plugged in the actual function coming from the left with x is less than 2. Plug in, I get 1. Then I do the limit from the right of my function, this guy. I plug in the specific one I'm talking about from the piecewise. X is greater than 2, I use the quadratic. Plug in, I get -4 plus b. Since I know the limit exists, I know that the limit from the left, which was this, the limit from the left, has to equal the limit from the right, which is -4 plus b. Both limits need to be 1 for the overall limit to exist. So I stated that right here, so go ahead and make that a note. The intended y value, they will go to the same place. All right, so right now I solve quickly, and I get that b is 5. So I know b is 5, but I still need c. That's part of the theorem, which says that the function value is equal to the limit value. Well, I know the limit value is 1 because the left and the right hand limit both equaled 1. And then the function value, I didn't really know what the function value was. I just knew that the function value was c. But because I know that the function value has to equal the limit value, I know that f of 2, which is the function value, has to equal 1. Function value has to be 1. And I already stated that the function value equals c. I know that c has to be 1. This is what's given. This is what needs to happen. So therefore, these two need to be the same. So our conclusion statement, if we're going to be continuous at 2, b is 5, c is 1. So go ahead and finish jotting that down. And then we're going to do one more quick example here. And we're going to see an actual AP problem. This is a really big moment for you guys here. 2003. This is question 6. There's always 6 free responses on the AP exam. They usually have anywhere from 2 to 5 parts. And for this one here, we have another piecewise function. We are trying to decide, is the function continuous at 3? So this is really similar to the first example we did. Your explanation, you don't want to think like, oh, I'm going to explain in a big paragraph like I'm in an English class. Your explanation is going to be your math work, and you're just going to have a really quick sentence at the end. So let's go ahead and start by finding f of a. In this case, a is 3, so let's find f of 3. F of 3, let's see, which one is defined for 3? Only this guy. So f of 3 will be the square root of 3 plus 1, square root of 4, which is 2. Now let's find the limit as x approaches a, which is the limit as x approaches 3 of our function. So in order to find the function, I have to do the limit as x approaches 3 from the left and the limit as x approaches 3 from the right of our function. So let's go ahead and do one at a time here. Has to be the function defined for values less than 3. So I'm going to use my radical. So that's the limit as x approaches 3 from the left of this. Direct substitution, always try that first. And I get 2. I don't have to factor or cancel or anything because I didn't get indeterminate form. Okay, limit coming from the right, I'm going to use this function whenever values were greater than 3. So now my linear function. Direct substitution works out fine. Oh, check it out, they're equal. So I can say the limit from the left equals, this is like basically your explanation, all in math talk. So limit from the left equals limit from the right, which implies that the overall limit exists. And we also know that the function value equals, and I should say it exists and equals 2. So the function value equals the limit value. Because the function value equals the limit value, we know that the function is continuous at 2. So just real quick, you would say since f of 3 equals the limit as x approaches 3 at x, which equals 2, f of x is continuous at x equals 2 by the definition of algebraic continuity. And they know basic abbreviations on the exam. All right, cool. So make sure you have this definition memorized. You're going to need that for the rest of the week when we practice all kinds of continuity. And I'll see you in class to practice. Bye.